Alright, so in this video I'm going to go over the solutions to the electrostatics and circuits test that you all took right after you got back from break. Please watch this video. You can skip through it if you feel like you understand some content, and skip to the questions that you feel like you really had no idea. So I'm going to start off by going through the multiple choice questions real quick, and then I'm going to go over the FRQs. So I'm going to try and keep this video underneath 6 minutes. I think, no, that's definitely not doable. Let's say 10 minutes, maybe. Okay. Question 1. Two small spheres of equal charges Q and are separated by distance d. The force exerted on each sphere by the other has magnitude F. If the charge on each sphere is doubled and d is halved, the force on each sphere has magnitude. We have to use a good old Coulomb's law here to do this. So the way that we would reason through this is to say, okay, initially, if the two small spheres have equal charges Q and are separated by a distance d, then it's just this equation, right? Q1, Q2, distance d. So whatever change happens, we have to look at the resulting electrostatic force as a factor of the original electrostatic force, right? So let's say 2 times Q1, Q2, and 1/2 times d. Let's see how that looks in this expression right over here. K 2Q1 times 2Q2 all over 1/2 d squared. So between here and here, K doesn't really matter, right? So K doesn't matter because it's the same. Here we have Q1, Q2 over d squared. Here we have 2Q1 times 2Q2, which is 4Q1, Q2 over 1/2 squared, which is 1/4 d squared. So really we have a coefficient of 1 here and a coefficient of 4 times 4 divided by 1 over 4, which is 4 times 4, 16. So the second sphere, the force on each sphere has a magnitude of 16F. So it should be D 16 times. Okay. It's because I think a lot of people made a mistake because they multiplied 2 times Q1 times Q2. They didn't do 2Q1 times 2Q2. The trick here is to note that the charge on each sphere is doubled, not the charge on both spheres as a whole is doubled. Okay. Two identical spheres are charged to plus 2Q and minus Q respectively and are separated by a distance d. As shown in the diagram, magnitude and force of attraction on the left sphere is F1. After the two spheres are made to touch and then separated again by a distance d, the magnitude of the force on the left sphere is F2. So the key here is to first figure out what F1 is in this situation. So F1 is going to be equal to K, and once again we're using Coulomb's law, without a doubt, 2Q times negative Q all over d squared. 2Q, negative Q over d squared. F1 is negative 2Q squared over d squared. Cool. Now let's compare this with F2. For F2, we know that we still got a K, but once the two spheres are made to touch and then are separated again by a distance d, if we have plus 2Q here and negative Q here, once they touch, this is a plus Q. That's a net charge here. Plus 2Q plus negative Q. The net charge is plus Q. That plus Q is going to split into two spheres evenly. So then we're going to have 0.5Q and 0.5Q. 0.5Q and then 0.5Q, because that net charge is going to separate evenly. Still separated by distance d gives us d, all over d squared. So then this gives us 0.5 times 0.5, that's 0.25, or 1/4 Q squared over d squared. So the only possible relationship between this first F1 and the second, the first force and the second force is that F1 has to be 8 times F2. That's the only way we get from 1/4 to 2, is if this is 8 times F2, which it is, because 8 times 1/4, it doesn't matter whether or not this is positive or negative. So the correct answer is in fact D. For 3, this is a pretty easy problem because all it's asking us to do is compare the electrostatic force from plus Q to A and then plus Q to B. So then this is just comparing a distance d versus a distance 2d. So we'll call this FA is equal to KQ, which is this plus charge, and then this big Q, it doesn't really matter, over d squared, versus FB is equal to 2d squared, which indicates that the force on B is 1/4 the magnitude of the force on A. Right? So the ratio of the electric force strength at A to the electric force strength at B is 4:1. So far we got D. Oh, oops, you couldn't even see that. Sorry. Right. I didn't even realize. Alright, moving on. Oh, there's no way I'm going to do this in 10 minutes. I'm going to keep going. Alright, when a negatively charged rod is brought near but does not touch, the initially uncharged electroscope shown in the diagram then leaves the spring apart. Okay, so negatively charged up here means that, I'll do positives and negatives. Positives will be red, and the negatives will be blue. So the positive charges are immediately going to flock to the top when that negatively charged rod is brought near it, and then the negative charges are going to be on the bottom, right? Now, so we know immediately that for the first situation, that rod is going to be, or the electroscope, the charge on the leaves is going to be negative, without a doubt. The charge on the leaves is going to be negative for this first one. So we can cross out A and C. So it's either B or D. Now, we know that in part 2, this rod is nearby. So all the positive charges are still going to be up here. The only difference now is that the ground right over here, the ground provides a path for negative charges to travel out. And so what's going to happen here is these negative charges are going to flow from the leaves all the way up. So as they flow, they're going to flow out over here. And so there's no charge on so momentarily there's actually no charge on the bottom of the leaves. That's why there's no deflection, because all of the negative charges are sliding up to the ground. So in that process, when the negative charges have left, because they've gone through the ground, there's no charge on the bottom. Now, once the rod is taken away and the finger is taken away, the only charges left on this rod are going to be the plus ones that were left over from over here. And because they're going to spread out on the leaves again, you're going to have negative in 1, positive in 3. Now, 5, this is asking us whether or not we recognize that Coulomb's law is, or sorry, the electrostatic force is equal and opposite on each of these spheres. So we know that the electrostatic force has to be equal in magnitude, and so immediately we can actually cross out A, C, B, and the only option left we have is D, which has to be correct. The electrostatic force between the spheres are going to be equal and opposite in magnitude. They're not going to be any different in magnitude, and they're going to be opposite in, or equal in magnitude, opposite in direction, right? Because if this is positive and positive, that's going to be a repulsive force. So they're going to be in opposite directions, and they're going to be equal in magnitude. That's the kicker here. All right, for 6. When two resistors with resistance R1 and R2 are connected in parallel, the equivalent resistance of the combination is 5 ohms. Which of the following statements about the resistance is correct? Both R1 and R2 are greater than 5 ohms. Both R1 and R2 are equal to 5 ohms. And less, okay, so we know that when you connect resistors in parallel, the equivalent resistance goes down, right? The more paths that the current has to travel means the less resistance the circuit encounters overall, or the current encounters overall. And so if the two resistors with resistance R1 and R2 are connected in parallel, and that means the equivalent resistance of the combination is 5 ohms. That means that if the equivalent resistance had to decrease, because there are multiple paths here for the current to travel, initially R1 and R2 had to be greater than 5. That's just how adding resistors in parallel works. We decrease the overall resistance, and so if you decrease the overall resistance and it's now 5 ohms, initially both R1 and R2 had to be bigger than 5 ohms. Number 7 was pretty tricky for a lot of people, and so let's take a quick look at what's happening here. So I'm going to draw, let's trace the current in problem 7. And this is if the switch is open. If the switch is open, what happens? If the switch is open, 3 light bulbs in the current shown are identical. So if they're identical, the current isn't going to discriminate between either of these branches, but we're not there yet. Switch S is close to cause bulb 1 to light. Which of the other 2 bulbs increases in brightness? So without the switch closed, let's see what happens. Current goes through here. It can't go through here because that's not a closed loop, so it'll go through here. It'll pass through 2, join this junction. It's not going to go back. It won't do that. It'll go through 3, and then it'll enter back at E, or at the battery. Okay, so we have two resistors in that circuit when the switch is open. Now, let's say the switch is closed, and I'll draw this current in red. Say the switch is closed. Now, if the switch is closed, what is the current going to want to do? Once it gets to this point, the current can actually split between these 2 points. Now, that means that for this section, right over here, the equivalent resistance overall has gone down, right? Because look at this. Now that we have 2 branches here, we can say that the equivalent resistance has gone down. Because now there's multiple paths for the current to travel. And so if we look at this from the perspective of V equals IR, if the voltage is the same, but the resistance has gone down, the current can only go up. This battery hasn't changed. The resistance overall has gone down because we've added another branch. And so the current overall has to go up. And so if the current overall goes up, then once the current joins right over here, this is now experiencing more current because the current stays constant throughout the circuit. So bulb 3 now experiences a lot more current. You can draw a lot more current than it did when the switch was closed. But when we look at bulbs 1 and bulb 2, those 2 bulbs are still going to split the current. Even though the current is greater, they're still going to split it. And so bulb 2 is actually not going to get more current than it did initially, right? Because initially it was receiving all of the current when the switch was open. So here's what happens. If you close switch, you decrease equivalent resistance and you increase overall current, right? And so bulb 3 is brighter for sure because it's just experiencing more current now, right? It's the only bulb in that branch. It's going to get all the current before it goes back to the battery. But bulb 2 is now splitting current with bulb 1. So although there's more current flowing through the circuit overall now, bulb 2 is splitting its original current with bulb 1. The current that it had originally now with bulb 1, and so it won't get brighter. It'll in fact get less bright. And so bulb 3 is the only one that's going to see an increase in brightness. This is a tricky one. Total equivalent resistance between points X and Y in the circuit shown is, well, let's find it. If this is 2 ohms, then we got to find what the equivalent resistance here is, solve for it, and then add it to that resistance. So let's see, 1 over Req, because we're adding these in parallel, 1 over 2 plus 1 over 2 is equal to 1. The inverse of 1 is 1, so the resistance overall is 1 ohm. Okay, cool. So this is 1 ohm. We add 1 ohm to 2 ohms, 3 ohms. Easy money. So the total resistance here is 3 ohms. Cool. Oh man, we're already at 14 minutes. Yikes, I knew I couldn't go over this quickly. Okay. Power dissipated in a wire carrying a constant electric current may be written as a function of the length of the wire, diameter d of the wire, and the resistivity P of the material. In this expression, the power dissipated is directly proportional to which of the following? Power dissipated in the wire carrying a constant current may be written as a function of the length of the wire. Okay, that's because P is equal to I times R. Now what this is saying is, okay, now let's take a look at R. R is going to be equal to, resistance is going to be equal to the resistivity times, there is a formula for this, resistivity times, well, what matters? Times the length, right? Because as the length goes up, the resistance is going to go up over the cross-sectional area. Because as the cross-sectional area goes up, the resistance is going to go down. Okay, so now, as the resistivity goes up of the material, the overall resistance is going to go up too. So, power dissipated is directly proportional to which of the following? The resistivity and the length. Because as these two go up, and this is just based off of the formula. P and L are both going to contribute to the power via resistance. Alright, now number 10. Which two arrangement of resistors shown have the same resistance between the terminals? Alright, well, let's just add these bad boys up. 2 ohms, 4 ohms, okay? This is, oh, we did this one already. This is 1 ohm. 1/2 plus 1/2 is 1. Reciprocal of 1 is 1. 1/4 plus 1/4, let's see. 1 over REQ is equal to 1/4 plus 1/4, which is equal to 1/2, right? 1/4 plus 1/4 is equal to 1/2. So REQ here is going to be equal to 2. And so resistances 1 and 4 must be equivalent. Select two answers, A and D. Cool. Alright, FRQs. 2 uncharged conducting spheres of equal size are held at rest on insulating stands or in contact with each other. A negatively charged rod is brought near sphere 1 but does not make contact. While the rod remains in this location, sphere 2 is moved some distance away from sphere 1 as shown in the diagram. What are the final charges on each sphere after they're separated? Cool. So just like in that previous problem, the multiple choice problem, when that rod gets brought here, the plus charges in this overall neutral rod gets brought here.
The plus charges are going to migrate over to sphere 1. It's going to leave the minus charges, and the negative charges are going to move over to sphere 2 because they want to get away from that negatively charged rod. The negative charges are going to be like, whoop, got to get out of there. And the positive charges are going to be like, trying to get closer. And so when these two spheres are brought apart, you know you're still going to have that distribution. So you're going to have the negatively charged sphere 2 and positively charged sphere 1. Final charges on each sphere. 1 is positive. 2 is negative. Justify your answer according to charging by induction. The negatively charged rod, you could say something like the negatively charged rod will, and I'm not going to write all of this out because I don't have too much time, will attract the plus charges onto sphere 1, and then will attract the positive charges onto sphere 1, and then repel the negative charges onto sphere 2. Once sphere 1 and sphere 2 are polarized, if they're brought apart, then they're each going to maintain the charge they had before they were, as they were touching, right? That's charging by induction. Now suppose that the two charged spheres now carry a charge of magnitude 8c for sphere 1 and 4c for sphere 2. The two spheres are brought into contact with one another for a time sufficient to allow them to reach an equilibrium charge. They are then separated. What is the final charge in each sphere? Okay, so we have 8c and 4c. If they're brought together, you're going to have a total of 12c, right? That are just floating around between the two spheres, but then that 12c is going to distribute evenly, so you'll have 6c and 6c. So then once the rods are separated, they're each going to have plus 6c, right? You could draw a picture, you could justify by words. They're each going to have plus, each of the rods are going to have plus 6c on them, the spheres. Two spheres experience an electrostatic force of magnitude F between them. If the magnitude of the both charges is doubled and the distance between the two spheres is halved, what is the magnitude of the new force between them? We already did this problem! Wow, I'm realizing this now. This is the same problem as this one over here. The charges on each sphere is doubled, the d and d is halved, the force on each sphere. Charge is doubled, d is halved. Charge is doubled, d is halved. Has to be 16F according to the same principles as we used for that first problem. Describe the motion of a small positive test charge that is placed midway between the two spheres. Indicate the direction of any force exerted on the test charge. Okay, so this is in reference to this problem over here. And so if we place a small positive test charge in between two positively charged spheres, then what's going to happen? That small positively charged test charge is going to experience a repulsive force from that sphere and a repulsive force from that sphere, right? So then the repulsive force is going to be equivalent on either side, and so the net force it feels is going to be 0. It's going to be no net force. The sphere remains at rest, or the test charge stays rest. Alrighty. I'm not going to do this one out. Basically, we have, you see voltage and you see current. V is equal to IR. We know that we want to figure out the resistance, so resistance can be the slope. You have a data set right here, y and x. So as long as you plot current in amps on the x-axis, you plot voltage in volts on the y-axis, you should get some sort of curve with a slope of R. And R over here will be the resistance. And so many of you plotted the points and then figure out the slope. And the slope was around 10 ohms. You looked at the rise of the run. That's great. That is exactly what I want you to do here. You linearized a data set and you determined the resistance based off of a mathematical relationship. Easy money. Okay? Moving on. Alright, final question on this test. We have a somewhat complex circuit. Now, we want to figure out what the equivalent resistance is of the three resistors. And so first off, we have some resistance here that's going to add to whatever resistance we have over here. We have to add these two resistors in parallel, figure out what that resistance is, and then add it in series to the resistor here to figure out the equivalent resistance for the overall circuit. So let's start off by figuring out what R1 and R2, the combination of R1 and R2 is. So because we're adding these resistors in parallel, we got to do 1 over R1 slash R2 is equal to 1 over 4 plus 1 over 12. This is equal to 3 12s, 4 over 12. So we know that R1 slash 2 is equal to 3 ohms, because that's 4 over 12. The reciprocal is equal to 3 ohms. Now, if find Req, we have to do R1 slash 2 plus R3. So if R1 slash R2 is 3 ohms, that's this guy right over here, plus 9 ohms, we get a total of 12 ohms. So there's a total of 12 ohms of resistance in this circuit overall. Now, we want to figure out the EMF, or the voltage of the battery. That means we have to use V is equal to IR again. And so we're just solving for V here. We know that I, the current, is given right over here, 0.4 amps. Why do we know that that's the current? Because the current is going to be the same throughout the main branch of the battery, and this is the main branch, so the current passing through this battery has to be 0.4 amps times the resistance, 12 ohms. When we multiply those two out, we end up getting, what do we get when we multiply those two out? You end up getting 4.8 volts. So the equivalent resistance is 12 ohms, the EMF is 4.8 volts. Now we have to find the potential difference across resistor R1. So VR1 is going to be equal to this guy. What is the voltage drop here? Well, we know that the, how can we do this? All right, so we know that now that we've found the overall voltage of the battery, so we know that the battery provides some voltage, 4.8 volts, right? That's the total voltage provided by the battery. Now, we can figure out what the voltage provided by this resistor is because we have some information here. V is equal to IR. And so here, I is 0.4, R is 9, and we can establish that the voltage drop across this resistor in particular is 3.6. That means if this resistor drops 3.6 volts, that means this branch has to drop 1.2 volts. How do we know that? Because the only way for the voltage to get back down to 0 is if this drops 1.2 and then this resistor drops 3.6. So VR1 is going to be equal to, and we know in parallel, the V up here is going to be equal to the V below. Like the voltage drop across both of these branches is going to be, or both of these branches is going to be equivalent. And so VR1 is going to be equal to VR3 V total minus VR3. V total is 4.8 volts. VR3 is 3.6. So we have a voltage of 1.2 volts dropped by both of the resistors of this branch. So we actually solve for the potential difference across R1 and R2 because it's the same, because they're in parallel. Alright, D. Determine the power dissipated in resistor R1. So the power is going to be P is equal to V times, what is it? V times I. Alright, so P is equal to V times I. Now in this case, and because we want to determine the power dissipated in resistor 1, we need to do VR1. So we already have VR1 from this one. We also want to figure out what the current is here. Now, I could do that, or I could just do V is equal to IR, solve for I is equal to V over R, and substitute V over R into this expression down here, because we know that I is equal to V over R. So let's do VR1 times VR1 over R1, right? Because I have all these variables, I could solve for the current, but might as well just do everything in one step. So VR1 times VR1 is equal to VR1 squared. So the voltage across R1, which is what we solve for here, is 1.2 volts squared over R1 is equal to 4 ohms. When we multiply those two, multiply this out and divide it by 4, we get 3.6 watts. That's the power dissipated, 3.6 watts. Sorry, 0.36. 0.36 watts. Now, finally, for part E, determine the amount of charge that passes through the resistor R3 in 1 minute. This is all about using the formula for current. So if we want to determine the amount of charge that passes through R3 in 1 minute, it helps to realize that Q is equal to, current is equal to Q divided by time. Right? Amps, which is what current is measured in, is just coulombs per second. So here we have amps is equal to some coulombs per second, and we want to figure out the number of coulombs that actually gets deposited in 1 minute. And so here we can solve for coulombs and say coulombs is equal to I times T, or the charge is equal to I times T. Here we know that the current is going to be equal to 0.4 amps, and we know the time is going to be equal to 0.6, or 60 seconds. So and because amps is in coulombs per second, we know that we can put this time in seconds. So 0.4 amps is coulombs per second. So 0.4 times 60 gives us 2.24 coulombs. Not 2.4. 24 coulombs. So Q is equal to I times T. We got 24 coulombs. All right, but video. Let me know if you have any questions. Good luck on your test tomorrow. You guys are going to kill it. I'm so proud of all of you for doing tremendous things all year. Check in with me after you're done. Bless up.